want to thank you guys for all being here with us today. Welcome you guys here to the first breakout session of SPFA 24. Appreciate all of you guys' presence here, and just excited to share a presentation with you guys this morning. I'm not going to read through this policy, but it's here for SPFAs and the rest of our benefit in some form or fashion. So
it's very important.
It's very important.
Please do not discuss some of these key aspects amongst ourselves. But why don't we then continue on?
So we'll just kick it off here. Today we're going to be discussing understanding and optimizing proportioner settings for spray foam application. For those of you guys that don't know me, my name is Seth Dodge. I provide tech support with natural polymers. I spent my career in the field working with crews, proportioners, equipment, and mainly just applying product. Been out in the field training guys. So what's great about this session today is we're going to offer some cool new insights into optimizing your proportioner settings that maybe it's something that some of us haven't thought about before, and the study that we're going to discuss will give some great context. So for today, why most of us are actually here is that we want to provide the safest and the highest performing product so that we can drive customer satisfaction and commercial success for our businesses and the industry. We're all here with the same goals in mind, even if we're from different parts of the industry, and we want to move this thing forward together. So with that, proportioner settings impact that goal in a few different ways. Applicator and customer safety is the number one priority that we have in this business. It's the number one thing that we want to drive the highest level of attention toward. And with that, when we pay attention to our proportioner settings, we make sure that we don't misattune them in a way that increases risk. Increases risk of exposure, ultimately risk of safety, and having potential liability risks as well. We want to make sure that we're keeping ourselves safe, as well as the building occupants, who we know increasingly we're seeing more and more chemical sensitivities out in our world because of the levels of exposure that we see to various polyurethanes and various chemicals. So we want to make sure that we're doing everything that we can with our settings and our application process to optimize what we're doing and reduce risk. Performance. We want to make sure that our physical properties are achieving all of those awesome spray foam characteristics that we sell when we go to the homeowners. Some of those characteristics include dimensional stability, R value, density, your open and closed cell content. But if we don't optimize our settings, we'll be compromising our reaction process and the curing process, and ultimately those factors of performance that we work so hard to explain to those customers and to our people that we're dealing with, that this is where our value prop really lies. And ultimately, we want to lead to the contractor commercial success. We want a safe, high-performing, and long-lasting product that will drive the value, reputation, and sustained success of our business. And ultimately, guys, we're all in this together. As contractors, as chemical suppliers, equipment suppliers, we're all pushing towards the success of our businesses and the industry together. And so that's what we're here doing at SPFA. That's what we're here doing in these education sessions. So for today, I want to just point out that we have this daily challenge that we have to deal with. We all have to engage the optimization of our product in dynamic and changing project conditions. We're site manufacturing a product which is different than any other process that we see in the building industry today. And doing that in suboptimal environments requires attention to so many factors. It would be an exhaustive list to go through all of the different things. You see some things you're familiar with on here with substrate, environment, equipment, chemicals. We could probably go for another 15 minutes just listing out a bunch more factors that contribute to the end result of the process. The point of this here is to say that optimizing performance is requiring optimizing proportioner settings. If we're able to do that, then we can get to the end result that we're really looking for, that high-performing product, that safe product, and the success that we want to achieve. So for today, I'm going to introduce to you here in a second Ernest Weissong, who did a 2023 CPI study where he worked with Evonik, some of the team at Natural Polymers, and Wood Industrial Health Associates to have a great illustration that really explains how some of these settings impact your product performance. So for that, please welcome Ernest.
How you guys doing this morning? Good. Great. Okay. Well, I want this to be an interactive session. It's not like we're preaching to the choir. But what I wanted to do is to talk about some interesting results that we got from this study. Because when we saw the end results, we said this could be very useful for contractors and helping you understand when you turn those knobs on your proportioner, what's really going to go on in the foam that you put into the wall, into the paddock, wherever. It was interesting, and so that's why that was the impetus for doing this. Talked to Rick Duncan, he said, okay, it'd be great, so let's jump right into it. I am a chemist by training, so we're going to have a little bit of chemistry. I hope you don't mind. But I think if you'll appreciate what's going on when you pull that trigger, it's pretty fascinating, a lot of stuff going on. But we're going to talk about some of the key fundamentals. We're going to go over the experimental design that we set up to try to find out what goes on when you work with the proportioner. We'll go through the results, which are very interesting. And then we're going to sum it up, take home messages. When you go out in the field, what are the things you should be thinking about when you're actually tuning up your equipment? And then, of course, we have to acknowledge some of the key folks who are helping out in this study. So let's jump right into it. Polymerization. How many of you out there are actually making polymers all the time? Raise your hands. Well, the question should be, how many of you are actually spraying foam? You're making polymers, all right? And this is what we get into with polyurethanes. I'll do this one up here. I have my little point here. Oh, Professor Otto Bayer. This is the creator of polyurethane back in 1937, and you'll notice there, gentlemen, where is your safety glasses? I guess back then they didn't have to worry about that, right? But we do. Bottom line is, though, that this gentleman figured out that if you reacted diisocyanates with diols, A being your poly or your diisocyanate monomer plus your polyol, you create a polymer, polyurethane. And you notice here that we've got ABAB, those polymonomer units. So, just imagine for yourself in this room right now, you've got two hands, hopefully. If you were to reach out and quickly grab each other, and then you're making polymer chains. This is what happens when we do polymerization. And the thing about polyurethane chemistry, it's extremely versatile. I mean, there's so many ways you can put together stuff, and it works so fast. This is why here in this wonderful venue talking about spray polyurethane foam. It's wonderful. So we're going to go through it and talk about it, but the important thing I want to illustrate here, it's ABAB. It's a 1-to-1 ratio. This is why when you make the foam, you should make sure you're always running with a 1-to-1 ratio. Because if you start putting these together in other ratios, you're not making polyurethane. I don't know what you're making, but it's probably not the customer maybe wanting. It's an important thing to think about. So, as I illustrated, we take polyol and isocyanate, and forgive me, I have to have a chemical structure here. This is the urethane linkage, and this is the backbone of the polyurethane molecules. One thing I do want to point out that's very important at this stage, isocyanates, which is what you start with, it takes a lot of energy to make those. It's not a happy molecule. It's very reactive. You take advantage of that to make the foam, and it goes fast. You don't want spray foam falling off the ceiling on your head. It has to go fast. So it has to be reactive. It takes, and I said, it takes a lot of energy. But guess what? When you react it with polyol, it releases that energy. It's exothermic. And that's why polyurethane, if you sprayed it, you know it can get hot. And I'll show you some data here that shows just how hot that is. But I just want to emphasize, it's an important safety consideration. It's something you should be well aware of. And here we see a person, of course, spraying foam. You take your resins, your polyols are put into something called the B component. That's pretty much all the stuff that goes into the foam except for the isocyanate. And it's different for each of the products, of course. And then there is the A component, the isocyanate. That's pretty much the same for all the components. But this is then how you make your polyurethane foams. So what are some of the key factors when you pull that trigger? Temperature. Temperature is very important, and we're going to talk about that throughout this situation. You have to have a certain level of temperature in order for the foam to want to react. If it's too cold, you're not going to be making foam properly. If it's too hot, you're going to have problems. As I mentioned before, ratio has to be 1-to-1 to make the polyurethane. And you really need to keep an eye on this. This is something that's also very important, and it gets into proportioner settings. Mixing. Just imagine for a second, as we're talking about this room, if on one side of the room, we have over here the A components, you guys are the A components right now, and the other side, we got the B components. How fast can I get you guys to go across that room, link up in the correct order, and make your polymer? Yeah. This is what you were doing every day. You're trying to get this to go. And if you're too slow, if you don't have a good mixing, guess what? You're not going to make any good foam. So mixing is very important. You're going to see this in the results. The other thing we have, of course, in the formulations are catalysts. And they are very important for enabling the linking of these monomers. In our formulations, we also have surfactants. Just like making suds when you wash dishes, you need something to create these surfaces to create the foam. That's very important. And then we have to have something to blow that foam up with, to expand it. Blowing agents. Let's talk about those for a second, because they're very important. We have either molecules that evaporate and create the foam, the expansion. Have you ever heard of HFOs, HFCs? Raise a hand. Anybody heard of those? Those are physical blowing agents, and they evaporate with the heat of that reaction, and they expand. And this is what creates the foam. The other one, of course, is water. Water can react with your isocyanate, and it creates carbon dioxide, which is also a gas, and that will create foam. This is, you ever heard water-blown foams, open cell. Sprays open cell foams. So you're making water-blown foams all the time. So those are your two main kinds of blowing agents. And the life of a foam, there you go, you mix it, you start to nucleate, you have all these tiny little cells waiting to go, and then as the temperature kicks in, that foam starts to expand, cells get big, and you create the foam. But it's a balancing act. Not only are you expanding, but at the same time, you're creating that polymer. It's a race. And you want that race to be matched. Because if you expand too fast and you don't have the polymer to support it, it's going to collapse like a souffle. Otherwise, if you polymerize too fast, then it's going to be locked up and it's going to want to creep and have all kinds of issues. These are the elements. If you spray foam, you've probably seen both of those elements. So this is where it's coming from. And there's, of course, as I talked about, the polymerization as well. There's one other thing I do want to mention here. I didn't put it on the chart, but let me go down. If anybody knows me, they know I love to go overboard. I can't resist it. And I didn't have a chance to put this in. There's a formula that I like to use, and that's called PB equals nRT. Anybody ever seen that formula before? Oh yeah, there's some physics. Ideal gas law. Pressure, volume, is equal to the amount of blowing agent, a constant, and temperature. Now, why is this important? Because the volume of foam, your yield of foam, is directly proportional to the amount of blowing agent, our constant, and the temperature. But it's inversely proportional to the pressure. Those who spray foam in Colorado or any high altitude know that your foam expands more at a higher elevation than it does at sea level. That's because the pressure is lower, makes the volume go up. If you've ever left the cap open on your closed cell blowing agent and your blowing agent evaporates because you didn't seal your drum, this goes down, yield goes down. If your temperature goes too high, and you're spraying your film too hot, yes, your yield will go up, but then if there's nothing to support it, it will collapse. So it's the only reason I point, this drives a lot of things that you see in foam. So if there's one thing to remember from today, this is an important relationship. Finally, you have to make sure after you've sprayed your foam that you have cured it and that you don't have any tackiness or things. And this goes along with consuming all the unreactive isocyanates. So I mentioned before, mixing is so important, and one aspect of this is viscosity. So, did you know that your MDI, if you kept your MDI and in the wintertime at 30 degrees, the viscosity is pretty much over 1,000 centipoids. It'd be like honey. Heat it up to 120 F, like it is usually in a proportioner, and now you're down into the olive oil flexibility. These sides are very similar to this as well. Why is this so important? Have you ever tried to pump honey? It doesn't go well unless you got some really fancy equipment. So the practical advice here is that some of the proportioners out there, they don't have enough heating capacity to bridge that large gap between the ambient temperatures and your set points. And so guess what? If you don't have that going on, you're not going to get the viscosity matching. You're going to have poor mixing, and you're not going to make good foam. So always precondition your A and B sides to an appropriate temperature that your system can accommodate. I'm sure a lot of you know this, but I'm just trying to reinforce some aspects of why it's been done. The spray gun. This is where it's all happening, right? Typical pressures are 900 to 1400. Your typical pressure or temperatures are 100 to 140 F. Inside your spray gun, things are all waiting to go, and then once you pull the trigger, you have high pressure impingement mixing with some very nice sophisticated designs that enable that mixing to go on and the reaction to go. And this I got from the SPF PCP training guide, and I'll put in a little commercial. If you are not PCP trained, you really should. They have a lot of great information and a lot of, it's excellent to go through this training and understand. And they'll teach you a lot more than I'm going to cover here. I just wanted to give a quick call out. So our subject today was operational parameters, and those of course are the controls that you guys have plotted out there. Particularly, it's usually your A temperature, component temperature, your B component temperature, your host temperatures, and your pressures. Now, this is just an example here. We have some of the what a manufacturer would come out and recommend. And what you'll notice here is if we're using a closed cell product and we're using a summer blend, that as the temperature of the substrate you're spraying on or the ambient temperature is going up, you generally will have to reduce the temperatures in your proportioner in order to match things, because it's a balancing act. The same thing that goes for the winters. Now, these are suggestions for starting points, and manufacturers have gone through and tested these. But as Seth indicated before, when you're out in the field, when you start in the morning, the temperatures are going to be different than they are later in the day. The humidity can change. So you have to be mindful of that, and you have to continuously, fine tune it. Because otherwise, I'll show you pretty soon, things will drift. But this is the starting point. The other thing is has anyone ever had spray foam formulations that are sort of at the end of their shelf life? You ever sprayed stuff at the end of its shelf life? Does it spray any different than it did when you first bought it? A lot of them do. And that's just because spray foam is dynamic. As it ages, some of the catalysts get tied up with acid that's being formed over time. The reactivity is going to change. You have to be mindful of that. And be mindful that when you're spraying, check the shelf life. And as you start to tune your system, you may have to kick the temperature up a little bit to compensate that reactivity because it's drifting. Okay, so when we got ready to do our study, we said the two main knobs that you would have to play with out there is pressure and temperature. That's usually what you play with, right? And the design we came up with was pretty much looking at the corners of what I call the operational window that you would typically use. And the lower corner here, we were using about 105F and 1,000 psi dynamic pressure. Then we would kick that up to 135F, but keeping the same pressure. But now we're also going to take that same temperature and we're going to kick up the pressure to 1400 and then combining both of them. So that's the box we're going to play in. Now, we didn't, it's hard to use commercial products because then you're starting to be a commercial for certain individuals. What we chose to do for this study is we used some generic formulas. And these formulas are pretty close to commercial products, but they're not quite perfect. You'll see that in some of the results, but they are great for illustrating the principles we're going to talk about. And we use both a closed cell and an open cell product. And we did those at ambient temperature, and we did those at 30 Fahrenheit. The folks at the Evonik facility have a very nice 10 by 10 by 10, 1,000 cubic foot test room where they can control the temperature very precisely. And this is where we were able to do these things. And we went through and tested both the open and closed cell foams at those different parameters. Now, as we started to do this I like to play with toys, and my colleague in the back there, Scott Schweiger, who remained nameless, right? He provided a very nice FLIR camera, one of these IR cameras that we look at the temperatures. And what we wanted to do is to get an idea of what's going on for the exotherm. So let me see if we actually get this to go. What you'll see here is the temperature in the foam actually jumps up very quickly to almost 170 Fahrenheit on the surface. This is an open cell foam. And then it starts to decay. That's pretty amazing. I told you foam has a lot of heat. Back of the envelope calculation I did was one set of foam will kick out about 60,000 BTUs of heat. Did you know that? That's enough to heat a small, like a 1,800 square foot home. So be mindful of that, and there it is. Now, you guys probably, when you get started, you'll spray test patches. You have to make sure that your reactivities are fine. We took one of those, and then after about 5-10 minutes, we cut into it, and you can see the interior core temperature was still up to 160 F after 5 minutes on an open cell foam. So hopefully you pay attention to a lot of the vendors that say, if you have to tear out off-quality foam, don't use your bare hands, please, because the foam stays hot for a long time and you will get burned. So I found that very interesting. So we took that, those videos and we then extrapolated what the data showed. At ambient temperature, when you spray the foam, within a few seconds, the surface gets up to 170 F. Okay, and then it starts to fall off on the surface. If you spray that at 30 F, it only goes up to 140, and then it falls off at a faster rate. It makes perfect sense. There's only so much heat that foam is kicking out. So if you start off colder, it's going to be colder. Why am I telling you this? Is because if you're spraying under colder conditions and the foam doesn't have enough time to react, you need to give it longer to react. Because if you're spraying foam under the cold, you treat it just like you did at ambient, there can be differences in the foam. You have to compensate if you're spraying under colder conditions, because it never sees the temperatures that it would at ambient. We also put thermocouples inside the foam. And the core of the open cell foam got up to 240 at ambient. And when we spray it in the cold room, it only goes up to 210. And then go down from there. So just, again, the foam that you spray in the cold is always going to be a little different than it is in ambient. And likewise, if we had sprayed this at 100 degrees, if it was July down in Louisiana, that foam would be hotter. It's all relative. And you have to be mindful of that as you're adjusting the equipment, and also when you're going to, how long you're going to ventilate. Because that foam stays hot for a long time. For a long time. So when we did the testing there at the Evonik facilities, we were using, they had a Graco variable ratio machine, but we were running at 1-to-1. Typical air purge gun, 4242 mixed chamber, and we sprayed up the foams in these stud cavities. We would cut out 12 by 12 samples, let them age for about an hour, and put them in Mylar bags, and we'd send them off to the lab for testing. There we go. Lots of fun. So what did we find? First of all, in this one, actually, let's see if this thing actually works. I hate to be up here on the left, but the guys don't mind, do you? At the lowest temperature and the lowest pressure, we see that the cell structure is kind of big, and the density is a little bit high, but as I'll mention, this formulation is not the greatest, but there it is. Now look at this. We've now keep the pressure the same, but we kick up the temperature. Cell structure starts to get a little tighter, but now we're starting to lose some of our open cell content. What do you suppose is going on there? As I said, these things are a race of expansion and polymerization. But if things start to go too fast, then the foam doesn't even have time to open itself, and it'll start to get tight. You ever seen that? You spray foam, and then it starts to retract on itself because it doesn't have the openness. So right there, too hot will cause this kind of problem. Now this is kind of interesting. We keep the temperature the same, 105, but now we're kicking that pressure. We're increasing mixing energy. And look at that cell structure. It's like twice as small, which is a good thing for foams, better things. Same temperature, we just gave it more energy, and now it's going. You have powerful knobs at your disposal. You know, temperature and pressure. Pressure gives you better mixing, it can to a degree. Temperature can accelerate reaction rates, it'll also reduce viscosity. Now, if you combine both of those, oh man, this is too much. Now we're not even opening, we only opened up 86% of the cells. Density's going up, the R-val's going up because the density is, but the cell structure is not the greatest. You don't want to be there. It's way outside of the operational window. So if I were to look at this foam, I would say the sweet spot is probably somewhere down here where you kicked it with sufficient pressure, but you're keeping the temperatures a bit lower. Okay. This is the relationship between those two. If we take this same foam and now we spray it at cold temperatures, oh, it's a little bit different. Those cells look a little bit nicer. If we now kick that temperature up, now we're starting to lose some open cell contact, but it looked a little bit better than the other one. Our densities are right on where they need to be. Here now, when we go at the lower temperature but higher pressure, we're getting good density, good open cell structure looks good. Even this one with the highest temperature and pressure, it's not so bad. So, under cold conditions, that would be more of a sweet spot for this one. It has changed. Actually, this generic foam is probably more like a cold season open cell, which I'm thinking it is out there. There it is. You see, hopefully you can see that relationship that just by changing those conditions, atmospheric conditions, how much now the proportional settings have changed. So now let's go on, and this is a summary that the sweet spot can change as a function of how your temperature change. Let's look at the closed cell system. Closed cells always have smaller cells. The density's higher, and here we are now at the lower end. It doesn't look so bad. Now we kick it with some more temperatures, and look at this. Oh yeah, the cell structure got a lot finer. That's good. But what is this guy? It's a blowhole, pinhole. That's not very good for your R value. That's a super highway to allow the blowing agent to leave, and your foam will not be giving good R values over the long run. So that's too much temperature under these conditions. If we just increase the pressure, we do get a finer cell structure. So here we are seeing a benefit from having more mixing. But if we now combine the temperatures and the pressures, oh, that's way too much. This is bad news. We have lots of bubbles. The cell structure is all over the place. It's way too hot, too much pressure. You wouldn't want to be operating there. So for this foam under these conditions, this is probably more like your sweet spot. Now if we go to the cold, now these cells are getting a little bit bigger. This is just not enough temperature and pressure to make a decent foam. However, now if we take the temperature up, we are seeing a better foam. Likewise, if we give it at the lower temperature, we give it more pressure, that's a little bit better. Maybe not as good as the other direction. And now we give it both of them, it's starting to push to the other side. So for this one, almost say you would want to have more temperature, but you definitely want to have good mixing. This is just estimates. These are generic foams. Your manufacturer of your foam should be giving you guidance as to where your particular foam needs to be. But I think the take-home message here is pay attention to what those manufacturers are telling you. We spend a lot of time. If you start drifting too far away, you become lazy, and I'm not going to give that much pressure. It's not that important. It can be important. It can be really important. So just summarizing this one, we see that, again, the sweet spot changes as a function of the conditions. So you need to be mindful as you're operating. The second part of this that we did is we went to that same chamber. We wanted to see what the impact on emissions would be. We just talked about the foam structure. Now we want to look at emissions. This kind of work takes a lot, and some of the manufacturers will go through this, and the ASTM method that does this. But what they do is they have to go into this chamber, set up 26 stud cavity surrogates, so to speak. You collect background information before you spray, and then you actually collect emission data during spraying, and then you wait for hours and sometimes days. Actually, for the new method, you go up to 3 days afterward with very little ventilation to see what's going on, what's coming out of that foam. This is how you establish the safe reoccupancies and re-entry times. Before I get into that, we also did some temperature monitoring, and again, for the open cell foam, we see that we got up to 220 F inside the cores, but most importantly, you'll notice that the temperature stays above 100 F for more than an hour, and it still stays out there. This is why, and so let me show you the chart. This is what we call the vapor pressure of one of the catalysts. One of the things in there that you may smell and come off, it can hurt you too. And you notice that at higher temperatures, the vapor pressure goes up exponentially. This is why it's important that you should keep your ventilation running for some time after you spray the foam, because that foam is going to stay warm for a long period of time, and during this time, things could be off-gassing at higher rates. In the closed cell foam is 4 times more dense than open cell. 2 pounds, right, per cubic foot? And it makes a lot more energy, a lot more heat. And so it gets up to at least 330 F at a 2-inch pass. And imagine now, this is why manufacturers say, be careful how thick you spray the foam, because that number keeps going up, gets up to 400 and higher, you start running into areas where it starts to scorch, and you can run into fire risk. You've got a lot of energy there. Be careful how you manage it. Here's another thing to be aware of, is that on the max side of that foam, the temperature we were measuring was 220 F. So if you're spraying over top of wiring or pipes or anything, it has to be able to withstand that temperature for a period of time. Otherwise, there may be issues. And in this case, the foam core temperature stayed above the ambient for over 3 hours. Again, be mindful how long you're running your ventilation. Longer is better. So, we quantified things that came off. In this case, we're going to talk about the MDI, the isocyanate. We're actually able to measure that and quantify. And this is kind of important. At the lower temperatures and pressures, we're getting probably 25 ppb of this guy. This is during the first 15 to 20 minutes of spraying. This is why you have to wear PPE, supplied air, or a respirator suitable for this. Now, if you go to the other extreme, and now you're spraying at the higher temperature and the higher pressure, the MDI that was coming off was 8 times higher. And we found that to be kind of interesting. Who would have thought? I just turned up the pressure and I turned up the temperature a little bit. Shouldn't make much difference. It made a lot of difference. Now, the point is, you should already be protected. PPE, right? People without PPE should not be in there. They shouldn't be around there for this reason, because you're creating an atmosphere that unprotected people should not be exposed to. But after time, it does drop back down to 0, which is what it should do. But during that spray time, you must be careful. And if you're running with higher pressures and temperatures, be mindful of that. For the VOCs, we saw a similar kind of relationship. And the VOCs we were measuring here were the 3 catalysts and TCPP, which is a fire retardant. It's a fire retardant we put in there to make your foam safe to use. And what you'll notice here is that, of course, at the higher temperature pressure settings, during application, the levels can be up to 5 times higher. Again, this is why you have good ventilation. This is why you should be wearing the PPE. There is one little subtle thing, though, I want to point out. If you look at over time, one of the catalysts now is still showing up above the baseline in the low pressure, low temperature. It's gone here. What could this mean? There are what things considered to be safe levels of these chemicals, but those don't always correspond to things that you can't smell. And this kind of a level here, you could still smell them. So be mindful as a function of how you're setting your equipment and how you're spraying. If you're not following the manufacturer's advice and having it properly tuned up, you could be leaving some VOCs behind that then maybe your customers are going to remind you of in the future. This is part of the reason, because you didn't get it out. In this situation, you were volatilizing it, heating it up, everything reacts good. Here, maybe you didn't kick it hard enough. It's still there. Just something to be mindful of. This is the open cell phone. In the closed cell, we saw a similar story, but it wasn't as dramatic. Frankly, because closed cell is closed. It doesn't have a surface area that open cell does. And the VOCs we also saw were a little bit higher here, but again, it's a lot different than the open cell. Open cell is a more challenging foam in that perspective. So I think we're going to sum it up here to say that obviously if you're spraying foam under cold conditions, it's going to make changes in the way the exotherms, the peak temperatures, and those can impact how the foam is formed, and also a little bit about the VOCs coming on. When you apply the foams at higher pressures and component temperatures in line with what manufacturers recommend, things go along pretty good. But if you have those pressures be too low or the temperatures go low, you can now be operating outside where it is. Has anybody ever heard of Green Guard Gold, and those things? Raise a hand. Anybody ever heard of these emission values? Yeah. I mean, those are methodologies to allow us to understand whether or not a product is going to have issues potentially in the field. And manufacturers, they apply these foams with the correct temperatures and pressures, and then test it. But now you can see that if you don't follow those manufacturers' guidance, you may not be in that realm. So follow those instructions, please. Multiple factors obviously go on and are driven by temperature and pressure behind the simple vapor refrigerant. So this is where we came up with on this one. So now I'm going to actually turn it back over to Seth if he's still awake. And since he's got the practical knowledge, I'm going to let him close this one up as to what we learned.
Thanks very much, Ernie. So that was awesome. I hope that provided some additional context for everybody here. Just looking at cell structure, seeing how the impacts of these parameters are impacting what we're working with. And again, that was a generic product, so that's going to vary between products. And for us applicators here, one of the things Ernie mentioned earlier, but we want to emphasize: know the guidelines from your product, and that's going to go to every aspect of the install process you want to pay attention to. We talked about that sweet spot and trying to stay inside of that sweet spot. We want to give ourselves tolerance in this process. With all the things that are working against us, to do a quality job on site, we really want to make sure that we have a little bit of forgiveness in there when there's factors that are outside of our control. So we want to encourage you guys to know your product, know your manufacturer guidelines, and take advantage of the resources that your technical support from your suppliers and from your manufacturers are offering you. Everybody is working on new stuff for the industry. Everybody wants to make sure that we're bringing education to the industry. And you guys, as applicators, as installers, have resources available to you. So take advantage of what you have, use it, call guys that you have for tech support, talk it through with them, and give yourself the best chance of giving a great install on every project that you do. Another thing is make sure that you adjust those application settings throughout the day. You know, we see big temperature swings, and most of us throughout the country, we're seeing, you know, climate changes that are, you know, different than what we're used to in, say, 10 years ago. You know, we're seeing it warmer, we're seeing it colder, we're seeing less snow, we're seeing more. So, you know, for many of us, we're seeing big swings in areas that we're not used to. So that's creating more of a demand on our adjustments, more of a demand on our applicator knowledge, because we need to pay attention to those things we saw in those targets, that these can move throughout the day. And hopefully that illustrated to you, as those targets move, if we're not adjusting with them, we can see a real impact to product quality. And the last one we have here is just check your work. We have some you know, simple ways that we can actually go in and just look. And one of the basic things that we can do is just check our phone. Break it open, look at the cell structure, and look at what that phone is telling us. Personally, my tagline is read your phone. Many of you have heard it, many of you say it. It's the absolute golden rule. Read your phone, look at it, see what it's doing, and it will tell you what it needs. We can also do field density checks to, you know, verify the quality of our install, and we can use core samples as well. We can check adhesion, lots of different things that we can do to make sure that we're doing a quality job on site, and encourage you guys to take advantage of all those things as well in your installs. So appreciate you guys being here with us today. Hopefully you were able to take something away from this that will benefit you guys moving forward from here. There's a number of people that contributed to this testing and to this presentation today, from Natural Polymers, Owens Corning, Evonik, Rickwood Consultants, and Intertech as well. So we appreciate all of their input on this, and thank you guys very much.